So we're going to look at the force diagram for the waiter's tray setup. I've simplified it just a little bit, so we're just looking at a block tied to a string. And we're interested in sort of the conditions where the string will stay taut. So string will stay straight. Because if it starts to flex a little bit, then that's when we know the block or the water, as the case may be, is starting to actually come down and landing on you, which is not so good. So when we look at this and try to look at how fast you need to swing it so that you don't get wet, for example, with the waiter's tray, then we can look at the force diagram. And so when we look at the force diagram, we recognize that we've got an acceleration down towards the center, so that's centripetal acceleration. So our acceleration is going to be v squared over r. And so as we increase v, then our acceleration goes up. And that becomes important because as we look at our force diagram, we have two forces that provide this acceleration towards the center. We have the weight, which is mg, and then we have the tension, right, the force of tension in the string. So in general, we have force of tension, if we call everything down as positive because everything's pointing down. So I have tension plus mg is equal to this m times the acceleration, right? This is my sum of the forces equals mass times acceleration, in this case in the y direction. And we've decided for this setup that this is positive y because everything's pointing in that direction. I just didn't want to confuse things with lots of extra negative signs. And again, that means in my equation, all of the letters are positive values. So as I look at this, I have tension plus mg is equal to, replacing this as mv squared over r. So notice this is a fixed value. That's just the mass of the object times g. But as I increase v, so as v gets bigger, right, it gets bigger, then what that means is that the tension must increase, right, to adjust, to make this equation still hold. In other words, if I make this much, much bigger, then I've got to make this tension much, much bigger for this equation to still hold. Okay, and this is, of course, a v squared still. So the minimum, the smallest v before things start to collapse, before your string starts to collapse and it's no longer tight, would be when your tension goes to 0. Okay, so if you take this equation as tension goes to 0 of T plus mg is equal to mv squared over r. So as we take that to 0, what we get is mg is equal to v. Now this is the minimum speed we can have over r, right? And still have, basically, that's the edge at which the tension is heading towards 0. Anything smaller than this v, you're likely to get wet. So notice that these masses cancel, and so your minimum speed, in this case, is just equal to g times r, or your v min is equal to the square root of g times r. So if you're looking at a radius of about 1 meter, then you can plug that in and you can find your minimum speed, right? So your minimum speed, if, let's say we have r equals 1 meter, then we put that in, that will be the square root of 9.8 meters per second squared times times 1 meter. Notice the units are going to work out because I'm going to have meters squared per second squared, and I'm going to divide that. And so as I look at this, I say 9.8 square root of that. And so that gives me 3.13 or thereabout meters per second now, because I took the square root of meters per second squared. So if it's 1 meter, it's about 3 meters per second that you need. If it's a longer, like 2 meters, right, then you change your speed appropriately, okay, for your minimum speed that you need. You can do the same thing on a roller coaster. That's, you go upside down. Obviously, we have harnesses when we ride these roller coasters, these loop-de-loop roller coasters, but hopefully they're designed so that you don't need it, so that you don't fall out. And so if we look at this, in this case, the force diagram for the cart, right, that's upside down, is that we again have mg, the people plus the cart, times g, the total mass, and then the other force acting on it would be the normal force from the cart. From the track, I mean, on the cart, right? It's pushing down on the cart. And so again, we want force normal plus mg to equal this ma towards the center. And it's the same, in this case, v squared over r. And so we can do the same analysis that says force normal goes to 0. That means you're just barely in contact with the track, right? As force normal goes to 0, that's when your contact with track goes to 0. So right at that point, that's where we're getting in the danger zone. So we would say mg is again mv min squared over r, and so again it's the same equation because it's basically the same setup, square root of g over r. These things are of course designed so that your speed at the top is much bigger than your minimum speed, so you feel good contact. And when you're riding a roller coaster like that, what you feel sitting in here, right, you're upside down, and of course you have your harness on, some kind of harness that's holding you in place, but you should feel good contact with your seat. If you don't, if you're going too slow, so if we set this up and we're less than our v min, so if our speed is less than our minimum speed, then there must be some kind of clamp of some sort that holds you onto the track. Okay, and often that's built in as well, that there's something that's holding you onto the track as well. And certainly you've got the harness holding you on into the cart, but then you need the cart to be latched in somehow also. So sometimes there'll be something sort of covering the wheels that keep the wheels from actually falling out of the track, just as an extra precaution. But if you're going fast enough, you don't need that. It's just like the waiter's tray. You're going to keep going because the object in motion wants to keep going. What you want to do is keep going that way if you're going around, the track this way. And so you want to keep going around the track. And so what the track has to do and your seat has to do is push you to keep you going around the circle. So you don't fall down, you just get pushed to keep going around the circle.